You can start away there, yeah.
Okay. Right. Well, good evening. My name's Paul Hawkins, and I'm going to give you a quick chat about a short historical perspective on international radio telecommunications. This is in the days before satellites and fiber optic cables, and mostly after Marconi's first efforts. Anyway, we'll move on. I'll try and keep it short.
Yeah.
So here we see two of Marconi's stations. His research centre at Poldhu, and one of the stations he built in Massachusetts, the USA, for transatlantic communications. Now, this dates back to the days of long-wave radio, of spark transmitters, and when Marconi was trying to compete against the established cable systems. And Marconi would believe that wireless would be a more economical route, and potentially have greater capacity than lots of unamplified cables around the world. Anyway, the transatlantic telegraph service didn't really get established until the station was built at Clifton, and in Canada, in Nova Scotia. But I'm not going to talk much about Clifton because you guys are probably more expert than I am, as it's in your on your doorstep. So we'll move along. As there, obviously, this is the early days of communications, and technology was advancing. And one of the probably a false dawn, in actual fact, was the invention of the alternator, the radio frequency alternator. So where you span a generator at a high enough speed, you could generate radio waves from an electric motor. So instead of the normal 50 or 60 hertz power supplies, you were generating 50, maybe even as high as 100 kilohertz AC waveform. And the Alexanderson alternator, invented by it was the development of Fessenden's work, and then developed by Ernst Alexanderson. And the picture there shows the station that Marconi built in Carnarvon in North Wales. So that was the first change of technology. It was still essentially an electrical system, not an electronic system. But as time moved on, the first tubes were invented by Fleming and DeForest. Delicate items, not very good for high frequency radio frequency, but good for low frequency audio amplifiers, and so they became useful for receivers and for detectors. And in doing so, they improved the sensitivity. So instead of using things like the magnetic detector, the Marconi magnetic detector, or a coherer, the diodes and the triodes that these early Fleming and DeForest produced amplified the signals, and that was the first move. By making the receivers slightly more sensitive, we didn't have to have a transmitting station in the west of Ireland, for instance, or a receiving station for that matter. It could be moved a little nearer London, which was the source of all the data, basically. That most of the telegrams were coming through London, and so they had very long lines. Now, as is so often the case, during the First World War, the development of valves or tubes advanced quite significantly. So by the end of the First World War, there were things like 2 kilowatt transmitting valves were invented, and this picture here shows one of the first valve transmitters. Is called a panel of valves.
Wow.
It was built by Round, H. Round, one of Marconi's assistants.
Yeah.
And it's just, as the slide says, 54 tubes producing about 100 kilowatts. So that was a major advance.
Wow.
And So we moved forward from there basically. In actual fact, I should say, in the words there, Westinghouse had built a tube transmitter in 1915 that actually achieved a transatlantic link. But I forget how many valves it used. It was a huge number of very small valves, basically, and the signal was heard in Paris. But anyway, so this is where electronics starts to appear. One of the things also that really turned radio into an electronic medium was the invention of the oscillator. That was invented by Meissner in Germany, Franklin and Round of the Marconi company at similar times, and they invented what was the first valve oscillator. So now you can generate the signal using an electronic device, a valve.
Yeah.
You can amplify the signal, and you can transmit the signal. So all of a sudden, transmitters and receivers were becoming all electronic.
Yeah.
And so just after the First World War, Marconi set up, this is one of the first stations he built in Essex, in actual fact, not too far away from the Marconi factory in Chelmsford. And there we've got a valve transmitter on the left and a valve receiver that was initially built for European telegraph services. Marconi was licensed to transmit to some of the European countries, and these were relatively low power transmitters in the 6 to 25 kilowatt range for Bern, Paris, Madrid, Vienna, and then latterly Glace Bay.
Yeah.
Although with the sort of power, with 25 kilowatts, the Glace Bay transmission was, at best 20 words a minute, maybe something like that, and then only at night when the atmospherics had calmed down.
Yeah.
So that was one of the first stations built with a transmitter Onger and the receiver at Brentwood. Moving on.
Yeah.
And in parallel, the British Post Office, who had an on-off relationship with Marconi, wanted to take control of their own radio capabilities, and they built a transmitting station at Rugby in the centre of England, Warwickshire, in the centre of England, and the famous transmitter was GBR, which actually produced 500 kilowatts from an all-tube transmitter for worldwide coverage.
Wow.
But only transmitting at 16 kilohertz. And of course, that transmitter remained in operation up to the beginning of this century, in actual fact.
Amazing.
Because it was used for naval communications. And it was a sad day actually when when its 820 masts were toppled in 2003 or 7, something like that. So so that was what the post office were doing. So we move on. Yeah, sorry. There we go. In the meantime, Marconi was frustrated by the lack of bandwidth and the capabilities, or the lack of capabilities of long wave radio, and he asked Charles Franklin to investigate high frequency shortwave and even VHF, and he and Franklin conducted a number of tests between Poldhu and Marconi's yacht, the Electra, and established some of the basic characteristics of shortwave propagation, leading to a conclusion that daytime communications with South America would be possible using shortwave radio. Wow. And of course, the benefit of shortwave radio is that you're able to build high gain antennas as opposed to just the lumps of wire in the sky, basically. Yeah. High gain antennas and lower power transmitters. So that changed the dynamic quite a bit. So here we see the first the first transmitter designed ultimately by Franklin, but by the Marconi company, and this is the first commercial shortwave transmitter. I've just read commercial short transmitter, and basically it had four panels, One was a sort of power supply and keying device for keying the thing. There were two panels for the two frequencies that were expected to be used on a shortwave signal, one for the day, one for the night, and then a power amplifier, which produced, at those times, it was about a 20 kilowatt input, about 11 kilowatts output.
Oh.
So that was, Franklin was the architect of the shortwave, what called shortwave beam system.
Yeah.
Now, Marconi won the contract for the shortwave beam system from the post office, who wanted to communicate with the British Empire, and they wanted shortwave beam systems to Canada, India, South Africa, and Australia, which, as I say, were part of the British Empire at that time. And there were a number of challenging conditions that had to be met, and if they didn't meet the conditions, then Marconi would have lost all his, the money would have, he would have had to have get rid of the stations and all the rest of it. And he was also allowed to build stations, or a station, for the non-Empire services, which were obviously South America and North America initially. Yeah. So, and this picture here is actually one of the ones at the Dorchester transmitting station, Dorchester and Dorset, which was operating to New York, in fact.
Wow.
So anyway, the post office beam stations were there was a contract. There were two transmitters, there were two sets of stations, or two transmitters, two receivers. One station did Canada and South Africa, and that station was located down here in the West Country at Bodmin, the transmitter and the receiver at Bridgewater. The station for South Africa and Australia was up in Lincolnshire, near Grimsby. So those were that. But the Dorchester station was built with the capability of taking on as many services as Marconi could actually fit in, really, and it really developed. So let's move on. Oh dear, I keep moving this the wrong way. I'm terribly sorry. This picture here shows the Franklin beam antennas and the beam arrays actually at Dorchester. Now, the beam array was a uniformly excited broadside array of collinear dipoles, which were basically vertical dipoles, or vertical collinears actually, so multiple elements within that, with a reflector, with a reflecting screen behind it. And then, of course, with so many wires, maybe up to 24 wires, if you get a very narrow beam because all the power is being pushed in one direction. Yeah. Very, very powerful beam, in actual fact. And this was the Marconi station at Dorchester, and the five masts on the left were used for the beam service to New York primarily. On the other side, you could use the other side of the mast as well, hang aerials on the other side of the reflector. Yeah. And that transmitted signals toward Cairo and the Middle East. And then on the left, in the foreground, there's two antennas, or two masts with a single antenna between there, and that was built for the service to South America, Rio and Buenos Aires. And then in the far distance, this is going on perhaps till in the early 1930s, I guess. You can see three antennas in the distance there, and that was for the Far East service we developed for service to Japan and China and other countries in like Burma and other parts of the Southeast Asia, basically. So those were the beam arrays at Dorchester. And those masts were 280-ish feet high, spaced at 650 feet between. So a five mast array was getting on for half a mile basically long. So it's a massive, and it's very complicated aerial because obviously each wire in the aerial, each of the elements was fed via a coax, and so you have a binary division of two into, so on. Yeah. So until you end up with one coax, back to the transmitter. And the coax, by the way, was a copper concentric pipe of about 3.5 inches in diameter, with the inner just under an inch in diameter to make 75 ohms, basically. So it was solid copper piping, quite expensive, really, but obviously low loss. So it was, although it was obviously the first of its kind, and it was, expensive by today's standards in terms of materials, and the fact that you've got these massive aerials, and they're only two. One of the two of the bays in that 5-mast thing would have been tuned to the day frequency, 18 or so megahertz, and the other two would have all been tuned to the night frequency, about 8 megahertz.
Yeah.
And you can imagine, that's got there's no sort of flexibility, really, because they soon found out that actually at different types of solar cycle, they actually needed to go to 14 megahertz in the daytime, and only perhaps 5 or 6 megs at night time. So they had to do things, and they found that the beam masts were actually the gain of the mast was had a lot in reserve, and so they could split the arrays and actually have more frequencies. And they ended up, this one had, 4 or 5 different frequencies, and it actually transmitted to Canada in the end, as well as New York. So anyway, and the South American one was split, because this is another clever thing, was split in half, because BA is in one direction and Rio is in a slightly different direction. And what they did, by altering the lengths of the feeders, they could make the beam skew very slightly, so it was pointing directly at the required station. Wow. So so really that one only had a half a beam basically per station. So anyway, there we are. We'll move on. This is the shortwave receiver invented by a chap called Matthew, and really it's a superhet receiver. One thing about it was a local oscillator was an LC oscillator, so probably drift a bit, and the IF bandwidth was relatively wide to allow for the transmitter, the distant transmitter, and the receiver to actually drift. So in operating these systems, the technicians were probably assigned to two transmitters at the transmitting station and to the receiving station, and they were constantly, there was no there's no automatic frequency control, or there's no crystal control, so you've got to keep the receiver in tune with the transmitter. Maybe as it warms up, the voltages are all controlled by rheostats. So the valve voltage, depending on the load of the radio station as well, might be going up and down. You've got to regulate. There's no little regulator chips to no 780 whatever they are chips to regulate. So the receiver, all radio stations, had quite a high staffing level. Yes. And when you think, of data, how much data has passed today, here we are sending data at 100 words a minute on the shortwave in average. And, you've got people in London at the telegraph centre sending out the actual telegrams, and then they key the transmitter remotely from London. You've got guys in the transmitters looking after the transmitters, guys looking after the receivers. So it's all terribly, labor intensive. Yes, I guess the word is. Now, changing back to long waves again, in the early 1920s, with the success of valve-operated transmitters and receivers, the British Post Office and AT&T in the United States started looking at the possibility of creating a long-wave radio telephone service, because obviously at that time, international telephones were restricted to unamplified or only audio amplifier wires, say from London to Paris or wherever, that kind of thing. So an intercontinental radio link had to, was quite an undertaking. And they did an awful lot of studies, and they were investigating what frequencies to use. And then when they settled on the transmit frequency, which was nominally 60 kilohertz, they had to then get agreement with other users, bearing in mind how narrow the long wave spectrum is and how many people were starting to use it. They had to get people to move so they could get a 3 kilohertz slot, basically, to squeeze the radio telephone channel through. And of course, they started all this work before shortwaves were understood and acknowledged, and just before the beam system. And so they continued this development. And the transmitter actually was operational in 1926, but didn't open to the public until January 1927.
Wow.
And as you can see, I just said in the words there, it was $60 for a 3-minute call, £15 at that time, $4 to the pound it was in those days. Wow. Can you believe? So it was a sort of, and that was in that money in those days. You're talking $60 was a month's wages for most people, I guess.
Crazy.
It was a rich guy's thing, but it was successful. Now,
amazing.
With the opening up of shortwaves for telegraphy, transmitters capable of amplitude modulated telephony were developed and started operation from about 1928. And this picture here is at Rugby again, as was the long wave radio telephone. Shows the radio transmitter for the Australian service, which I think opened in 1930 or thereabouts.
Yeah.
What I was saying about the transmitter technician having a lot of things to adjust. If you look at that transmitter, you can see, I think you'd lose count, but you see the number of knobs there are to twiddle there, basically.
It's like Concord or something.
yeah, absolutely. And of course it was, really. I mean, it was so they as a joke I said, nearly as many on my Yaesu FT1, basically. But anyway, so that was when they opened a telephone service to Australia, which was quite a major thing, really. And transmitters got better as time went on. So a little later in the 1930s, by the next generation of shortwave transmitters had appeared. So that rather open cage shortwave beam transmitter that I showed you a couple of slides ago was now replaced by transmitters that have a kind of familiar look, basically, all panelled in with meters and stuff. So you've got the gentleman there is in the picture. He's adjusting the voltage on the power supply regulation thing unit, and then you've got a 3.5 kilowatt transmitter, which is the first smaller box, which was capable of operating by itself, actually, but then with a 25 kilowatt power amplifier bolted on the end, and the larger one. And this was a SWB 810. And in the business, SWB we always called them swabs, basically. That's just what they were called. That's a swab 810. And those transmitters, they were installed in the late 1930s, and at some of the stations, Dorchester in particular, which is where I started work, those transmitters were still in operation right up to meter 10 minutes. God.
We'll keep going, and we can reconnect if you want.
Those transmitters were still in operation up to 1979 when the station closed. But anyway, doing telegraphy work. The next great development in shortwave radio was the rhombic antenna, because up to this time, all of the antennas that were developed by the post office and by Marconi and Franklin and so on and so forth were single frequency tuned antennas. And there are a number of antennas. The post office, British Post Office, used Walmsley, I think, was one of the designs, and then in America you've got people like Edmund Bruce. But he came up with this diamond-shaped antenna. So there's a few iterations, but it ended up looking like that.
Yeah.
The rhombic antenna, which is wideband, relatively wideband, reasonable gain, obviously not as high gain as a beam antenna. It's one of the compromises. But of course, by the time that these antennas were put in service, higher power transmitters were much more easy to manufacture, and so this was a very economical antenna, because you didn't have, you just got that. I mean, this antenna shows two rhombic antennas, one on the larger one at the top of the mast, which would be used for the lower frequencies, maybe 10 megs down to 7 or 8 megs, and then the smaller one strung between, which would be used for the day frequencies, above 10 megs, 10 to 20 megs, megahertz, basically. So you've got a very economical antenna, can do any frequency within a reasonable bandwidth and fairly constant gain. So, and as I say, with the improvements in electronics, the receivers are more sensitive, the transmitters are more powerful. So, dialing back a bit of gain on the antenna was quite was acceptable.
Yeah.
Just a slightly side thing. We always think of radio stations, people tuning radios and this, that, and the other, and all the rest of it. But in order to keep a radio station running, you've got people painting masts, and you can see in the left picture, there's guys on a very rudimentary platform that is on the ground. There's a little winch, and they're winching this thing right the way up to 280 odd feet. And these guys are painting, because we haven't got galvanized or stainless steel. These are angle iron masts, basically.
Wow.
And so they need painting with some sort of bituminous paint.
Yeah.
And I think each mast used about 250 kilograms of paint, basically.
Wow.
So it was a bit of a job. So that was one of the jobs. And then the other pictures, there were lots of motors and generators. Obviously, most of the radio stations were built in rural locations for obvious reasons, because of reduced noise and stuff like that away from cities. So they had generators, and the bottom picture is the technician there is servicing one of the main generators. And so the Marconi stations, they had generators that produced, some were 90 kilowatts, some were 150. And they produced 400 volts, a 400-volt generator. You then go to the other guys at the top. You had motor generators, which then converted that basic 400 volts into whatever is required, whether it was 18 volts for the transmitter valve filaments or 10 kilovolts for the transmitter HT. So there were lots of motors, and there were as many people looking after the generation side of power and the power side of it, and the maintenance and operation, as there were fiddling around with the transmitters. So it was a fairly major thing. So I'd like to give these guys credit, because they kept the show on the road, basically. Obviously, at a receiving station, the generators were a bit smaller because the power requirement was a lot less. But also, at a transmitting station like Dorchester, that ended up with about 20 transmitters, 20 transmitters, 25 kilowatt output, required quite a lot of generator power.
Yeah.
So as I say, and the noise, I mean, the conditions these guys had to work in. I mean, the outside guys, you can see, have got no safety gear, basically, overalls and cloth caps, probably hobnail boots. Workers inside have got no protection against sound, basically. And you can imagine, you've got a generator hall with four generators all pounding away.
Very loud.
It's a very noisy environment.
Yeah.
Just briefly, during World War II, just another social comment, basically. the guys who were on shift in the powerhouse or in the transmitter halls or wherever the receiver was, all at Dorchester and other stations, they formed home guard units to guard, to do whatever the home guard did during the war. Dad's army, basically.
Yeah.
But at the receiving stations, the shortage of manpower meant that they started recruiting women, because up to that point, as was so many industries in the world, I guess, certainly in the UK, anything new and technological was very male orientated. So these young ladies were trained on operating all the equipment at the receiving stations, which was a step forward for the female gender, basically, which is a good thing. So, all these things change. There we go. Right, moving on. After World War II, telecommunications had been at war just as much as materially people had.
Yeah.
And obviously, during the war, there was a huge growth in telecommunications because of all the logistics that the government needed from Britain's on the forefront of Europe. Where you've got troops coming from America, you've got supplies and goods coming from America, all the little ships that brought stuff over across the Atlantic, and then obviously we're communicating with Canada and Australia in particular, and we're very reliant on all the materials and things that were coming. So there was a huge growth of traffic. Of course, after the war, a lot of the infrastructure for telecommunications, especially in Europe, had been ravaged, basically. So there were a lot of transmissions required to European capitals. So you had radio services to Paris, to Madrid, Lisbon, Athens, Rome, basically, because all the cables had all been devastated by what went on during that period. So new transmitters required, and the stations were a lot of the stations were refitted. But of course, the other change that happened in that post-war period is that all the radio services, all the international services in the UK were nationalised. We had a Labour government come in 1948, and obviously they nationalised all sorts of things, power generation, water supply, and everything else. And telecommunications was one of those things. So the post office, which had been operating some radio stations, Rugby and so on, now the post office had all the Marconi stations as well. So that was interesting. And the post office invested a huge amount of time and money. And in this picture, there's new Marconi shortwave transmitters installed at Rugby, and new ST and C transmitters installed at Ongar and at Dorchester.
Wow.
A minute to go. Obviously, we're still in the valve period, but receivers became quite sophisticated. And this is an example of a receiver produced. The one on the left was actually designed by the post office at Dollis Hill, and then commercially put in production by companies like Mullard. And that was a telephony receiver there. And then on the right is the Marconi receivers that were around at that time. And they did a whole range of receivers for telephony and telegraphy. And they had diversity connections, so you could connect them to two antennas, which would then choose whichever was the best signal. I didn't mention, but a thing called space diversity reception, because multipath fading never doesn't usually occur at the same physical point, or at more than one physical point, because of the nature of fading.
Yeah.
And so if antenna was experiencing fading, the other one still had a good signal, and so these receivers could automatically swap between which was the best signal.
Wow.
So I've had experience with these receivers. They're pretty good. They were pretty good in actual fact. As I say, they were still in service in the 1970s when I was at a receiving station. But they were valve. They had a relatively low IF, so they had a tuned RF. So it's that the generation of technology when you had a tuned RF, a low frequency, intermediate frequency, around about somewhere with 2.6 to 3 meg, something like that, in those, depending on whose manufacturer. Whereas when we went on into the 1960s and the invention of the transistor, we ended up with synthesized transmitter receivers with a high IF up at 30 some odd megahertz above the HF, with just bandpass filters in.
Hello? It's gone, is it? Hello?
Hello.
Yeah, it went quiet there for some reason.
I did, didn't it? Yeah. My internet's still working okay. Oh, now you. Sorry, you've got to re-host me again.
1 second now. Oh, make host, yes.
I'm the host, yeah. Okay, we're good.
I don't know what happened.
No, I don't, But just a glitch in the in the email, I should think. Anyway, so yeah, these receivers, they weren't so nice to operate, really. Because they were also remote. The next picture will show that. I'll get it to, there we go.
Oh, yeah.
So this is the control centre at the receiving station at Beerley, which is near Stratford-on-Avon in the south of England. And I worked there for 3 or 4 years.
Wow.
And all of these semiconductor receivers, those are the control panels on that other chap is so you could just plug your phones in and just listen to what the receiver was, rather than them to walk around to the receiver to check on it. And they also had little signal strength meters on the panel, so you knew if the signal was getting weak and if you needed to ask for a different, change of wave. So
very interesting.
Yeah, I sat there many a time listening to all sorts of things. And of course, synthesis moved into the transmitter world as well.
Yes.
And 1969 there at Onga radio station, you've got these made by STC, fully synthesized transmitters. So rather than having 6 crystal controlled pre-tuned frequencies, you could now just type in the frequency you want and it would tune to it, basically.
Wow.
So it's fully automated, and if you look down the end of the room, you can see some feeders, sort of coax feeders.
Yes.
That's a switching matrix, so it could all be controlled remotely, basically. When I say remotely, at a control desk, basically, somewhere else in the room. So you didn't have to get up and do anything, basically. And of course, these are now independent sideband. They've got 12 kilohertz bandwidth, so you can have 4 telephone channels or a mixture of telephone and telegraphy.
Yeah.
And yes, well, terminal equipment, not very interesting in a funny sort of way, not so quite so. But telegraphy moved from Morse code, which was still in use certainly through the 1950s and from some locations.
Yeah.
But teleprinter systems, and then the teleprinter systems moved to ARQ, detection of error correction. So, as I say here, you've got telegraphy equipment which can pass 6 or 12 channels in a 3 kilohertz bandwidth. So you can, and with the error correction capability, and now you've got the possibility, or now had the possibility of actually connecting it to the telex network, basically. Wow. So subscribers could actually almost dial directly. On the other side is a piece of equipment that enhanced telephony. It's called Lincoln packs. This was another system that automatically compressed transmission and decompressed on reception.
Yeah.
The speed amplitude, and by doing so, it raised the average transmitter power, and because it operated at the rate of your syllables when you were speaking, it tended to remove or tended to mitigate some interference type issues, because and there were plenty of very often you had a teleprinter, especially in the evenings when signal propagation changed and the signals were getting weak, and you could hear to the side, you could hear a teleprinter or something interfering, and the international operators would come through to the desk and say, "Oh, such and such a station is sounded a bit noisy," and then you could hear this teleprinter, so whatever. but
fascinating.
It mitigated it, basically. Yeah. And I don't know if I can do this, but now we've got time actually. But this is what, and I don't know if you've heard these sort of signals. It's if it worked. There we go. This is 96 baud ARQ, so that's 2 teleprinter channels. Sort of transmission that was generally used from cable and wireless overseas stations. And then you've got all right. I can stop in a minute. But that's a 12-channel telegraph system. So within that, so you can hear the difference.
Yeah.
And then, and one of the things that I always used to like listening out for, every station had a call band. When you started to schedule in the morning or whenever it was agreed, you had a call band, and I'll do the London one first. So this is the one we used to put. Actually, this is an older one. There was a different one when I was doing it, but this is quite a decent one. And that's what the signal would have sounded like at the distant end. On that particular recording was taken on the Amman service, Amman in the middle in Jordan.
Wow.
They didn't have it. They didn't have their own what we call test speech.
Yeah.
So all they did connect back our test speech, basically. So you get that's a double hop HF link, and that's what it sounds. That's really gives you an idea of the quality of the sound. And this is in the days. And there were, you could tune around the bands and hear all sorts of stations. Obviously, by the time I was involved in this, New York had gone to cable, as far as we were concerned. Although, but we had about a couple of dozen locations we transmitted and received signals from. So by the 1970s. Oh, let's go back 1 minute. By the 1970s, obviously, satellites were starting to take over, and the sort of countries that were still using HF were either they were poor countries or countries that didn't have very much traffic, so they couldn't afford the expense of a new satellite terminal wasn't justified.
Yeah,
I mean we had like one channel to Kabul in Afghanistan. That was a horrendous circuit. That was they were, and also to the Falkland Islands and to Harare. Well, it was Salisbury then, Rhodesia, but Harare, Zimbabwe, basically, and a few other places.
Wow.
And Gibraltar was one.
Yeah.
Because we had out to Gibraltar because General Franco threatened to cut the cables, the telecommunicate in his, in his little spat with the UK. So we had a radio telephone service, and anyway, there were several interesting ones that some were reliable, some were not, basically. But it was, but you get when you're working these long distance HF circuits, it gets in your head, basically, and you get the feel. You can hear the ionosphere, you can hear the sounds, and you know what it, kind of. It's, I don't know. It's just something. It's just a bug that bites you, basically. So anyway, that's just a few of the sounds of HF radio.
Very good.
There was still. I've got quite a few recordings of test speeches from all sorts of other. Because obviously, at the same time, London was a communication centre to its interests.
Yeah.
New York communicated to its commercial interests, and then you had Paris in particular, which still had a lot of colonial connections, and then Moscow, of course, who had all sorts of connections to everywhere. So there were lots of stations on the air, basically. You could tune through the HF band, and you were coming across these stations, all the way up. But after probably the early 1980s. Satellites. I think the last HF service the UK operated was the Falkland Islands, and that finished in 1983. Wow. That was the last. And the last HF telegraph service was actually an order wire to Moscow. In actual fact, and that finished about 1990 after the end of communism. So it's interesting, really, why these things, Some stations, as I say, I use the old colonial term, Salisbury, Rhodesia, was subject to sanctions because it was it hadn't given up colonialism, and so they had to have HF radio. So there's all sorts of reasons why people were the dregs of HF radio, But at one time, back in the 1950s, there's probably 150 channels of HF from London being operated at any one time. So so that's really the story.
Great, thanks, Paul. That's you've really covered. We've ran through the 20th century there. With wireless telegraphy and it's it's all in your book, Point to Point, which is a brilliant book. I always flick through it and. It was time it was written. It was a good job you came along and recorded, because this was at risk of being lost. This story, as you said,
very much.
It people had I think I've seen you mention before. People had skimmed over Marconi's 1901 transatlantic leap to the Telstar, and everything was kind of blank and forgotten. But you've done a great job at bringing it all back.
Thank you. Yeah.
And the book Point to Point is still available. It's a great book. Yeah, I love it.
It created, amongst the staff, when the radio station started having to close, people were being made redundant. Yeah. Some of the stations, like Dorchester, moved over to the maritime service, because the maritime service continued to grow for another 10 years anyway. So that gave it an extra life. But obviously, people would spend there were lots of people not old enough to retire, for instance.
Yes.
Spent a lot of years in HF, and they didn't want to move to satellites.
Yeah.
But the irony is that satellites have gone pretty much out of fashion because of fibre optic cables. Fibre optic cables. Yeah. I forget now. The last time I looked, it's over 100 terabits. I think the North Atlantic.
Is it?
The North. Something like that,
Crazy,
and of course satellites, could do perhaps a couple hundred megahertz or megabits, but they couldn't compete against fibre optic cables. So at the time, when I worked at a receiving station, that's when I really got my interest in it, because I listened to radio and I realised what was happening, and but the management weren't really interested. They didn't really do much in the way of commemorating the stations that were closing or the service.
Yeah.
I thought this is going to be forgotten about. So I started making it. Took me nearly 30 years to write that blooming book, you know.
Well done. It's a very good book, and it's preserved now for the rest of the time. Thanks to you.
Yeah. Anyway, so I don't know if you've got any other questions. As I say, that's my final
I
slide.
don't really, Paul. That was a great talk. You've covered everything really, and thanks for I wanted to do this for Marconi's 150th birthday, which is coming up.
Yeah.
Which is now this month, and so thanks. It was a good time to do the talk. I think your point to point.
Okay.
And it was lovely to meet you virtually. And
indeed,
I'll end the Zoom, but I'll stay in touch with you. I'll send you a message very soon